All right, so let's talk about your lab report for the thermochemistry lab. A lot of calculations for this one. You also have to have graphs. So there's a lot of information to take in. So you might have to look through this and think about it for a while. But page 1, lab rubric for thermochemistry, found in Canvas. Then you've got lab report form. You can find this on the chemistry lab site. And now you're going to have to generate 4 graphs. I don't mind if they're on separate pages or they're on the same page, as long as you can extract the data from them, because you're going to use that. It's temperature in degrees Celsius versus time in minutes. I'm picky about axes. They need labels both in units as well and a title. And this is roughly minute 4. I'm going to show you how to do that in a second. Pages 7 on, I want all of your calculations. Nice, neat, easy to follow, legible. Because remember, a happy professor is a happy grader. So you want to make sure you have those calculations easy to find. Last page, carbon copy of your data. So let's talk then about this graph, because the graphs are going to help us do the calculations. And what you'll do is you'll start off, for example, you'll have a few points just at room temperature. And then at minute 4, you mixed your 2 solutions together, so you may not have a temperature time data for that. And then you'll end up with data that might look like this. And once you got those 4 points that are fairly similar in terms of temperatures, then you know you're good to go. And what you're going to do in order to find your change in temperature is you're going to use a straight edge. You'll print these out. You can do it on Excel, but you can also print them out, because some of you, I know, are still learning Excel. And you'll draw a best fit line here with your straight edge. I will not include that point because the temperature is still changing. Once I see, though, that the temperature isn't changing, I'm going to do another line across there. And again, you'll use your straight edge. Now I'm going to bring that line all the way across, and of course I've got it here. And then this change in temperature, that's your change in temperature that you're going to use for your calculations on that. So look for that. And then we're going to go now to the actual overhead so that you can look at this. Now I want you to see this data. You'll see this information right here. It tells us what the density of water is, the specific heat of ammonium chloride, and so forth. You're going to use this information to help you do the calculations. I'm going to go through 2 reactions and show you how to do calculations. The first one is ammonium chloride, and it asks you for the mass of the solid. That's just the mass of the solid itself. The mass of the solution here, though, is going to be roughly 52 grams, because that is the water plus the ammonium chloride. The same is the case for the sodium hydroxide. It's going to be roughly 52 as well. Your delta T comes from your graph. And you'll have another delta T for this graph. And now we're going to talk about how do we calculate delta H for heats of solution. So let's come to the board. The first one you had was ammonium chloride, and we're going to talk about this. So we want to get delta H. I'm going to make a notation. Anytime you're using calorimetry to find delta H, or the change in enthalpy, you're going to use the heat, Q equation, divided by the moles of the limiting reactant. So in order to go from Q to delta H, you have to divide by the moles of the limiting reactant in order to get there. So make sure that you keep that in the back of your mind. So let's come here. So since we know that we have to ultimately, our goal is to find delta H, that means we've got to start with this Q equation, our heat. So the mass here, remember this mass is actually referring to the mass of the solution, because it's not, if we had just ammonium chloride or just water, nothing happened. When we put the 2 together, we saw a heat change. So for this, we're going to start off, and I think the mass that you began with for this one was roughly 2.5. And so for me, I massed out 2.51 grams. Again, that's just my ammonium chloride. And then I added 50 mils of my water. And it tells us that the density of water is 1 gram per mil. So I'm going to multiply this by my density. I made a really big L there. There we go. And then that way, I'll have the 50. So this whole section is the mass of my solution. Then the next part, I'm going to go ahead and erase this delta H, is the specific heat. Now this specific heat, we're going to look to our diagram, so let's shift back over to the overhead. And it tells me the specific heat of ammonium chloride is 4. So I'm going to use what it gives me. This is coming from a table. So I'm going to come back to the board, and so I'm going to have 4.00 joules per gram degree Celsius times delta T. And your delta T comes directly from your graph. So you'll have some degrees Celsius there that you'll have to fill in after you make your graph and you derive your delta T from it. Then, now you have your heat in joules. And your report form wants that to be in kilojoules per mole. So you've got to make a conversion to kilojoules. And now we've got to get from heat to heat per mole. So again, remember, delta H is equal to Q divided by the moles of the limiting reactant. So we're going to take this heat, Q, plug it in here in this equation. Now to find the moles of limiting reactant for this, you'll have to think back to the lab. After you pulled the lid off your calorimeter, I hope you remember that there was no ammonium chloride left, but there was plenty of water. So that tells us that the ammonium chloride was completely dissolved in the process. So that means that the ammonium chloride was my limiting reactant. So from this, we intuitively get the ammonium chloride as our limiting reactant. So you started off, we know because of that, we can use and begin with 2.51 grams of ammonium chloride. Now again, this needs to be in moles. So we've got to do a conversion, mass to mole conversion of ammonium chloride. And again, this would come from the periodic table, and you've got to find that mass for ammonium chloride. Once you get that number is going to go there, and finally you have your delta H. Very, very important thing to note. You've got to figure out sign for delta H. It doesn't come directly from your chart. So the sign for delta H, what happened? Now remember, you had your flask, and you've got to think about what happened in the flask. And remember, you have your thermometer. Your thermometer is measuring what's going on in the surroundings. And this is your system within. So again, in lab, you talked about this, or you should have been intuitive and thought about it. You will have to assign the sign for this. It's either absorbing heat, the system is either absorbing heat, which is endothermic and positive, or it's giving off heat. In the ammonium chloride, think about what happened. Did this thermometer, did your temperature go down? If it went down in the surroundings, that means that the system was gaining heat, and therefore it was endothermic and positive. So that's something you'll have to assign. Don't forget it, because those signs are important. That is just one calculation. Your sodium hydroxide, you'll follow the same pattern as you did this one. So now, let's talk about one of the other reactions. Let's talk about 3 or 4. We're going to go to reaction 3. Now for reaction 3, I'm just going to glance over here. We had sodium hydroxide aqueous plus hydrochloric aqueous. And of course you've got your balance, and I think it's sodium chloride plus water. So there's our overall reaction. Now for this one, we've got a little bit more work. And again, our goal is to find delta H. We still start at the same process. We still have Q is equal to M times S times delta T, because it's from Q that we can find delta H. Again, this is the mass of my solution, not just of the sodium hydroxide and not just of the hydrochloric. And just so that I make sure I'm using the right volumes and so forth. So you had roughly 50 mils of sodium hydroxide and 50 mils of hydrochloric, and you added them together. Now we're gonna look briefly here at the overhead again, and it tells us that the density of the sodium chloride produced is 1.02 gram per million specific heat. Now there's an important thing here. Now notice the product of our solution was sodium chloride. So we're making an assumption that it's sufficiently dilute enough that everything that we're gonna base our heat on is gonna be based on sodium chloride. So therefore I'm gonna use this density and specific heat in my calculations. So now we're gonna come back to our calculations. So we used, and this may vary for you, you use what you did in the graduated cylinders, but I used 50 mils of each. And I know that it tells me to assume 1.02 grams per mil. That calculation is the mass of my solution. For the fourth one, it's going to change a little bit. You have the volume of hydrochloric, you have the mass of sodium hydroxide, and you have the volume of water. Don't forget that. You've got all three. So, but for this one, we just have the two volumes. Then we use specific heat. It tells us to use the specific heat of sodium chloride. And then, of course, we have our delta T, which you will have to get from your graph. And lo and behold, we have joules, which we have to convert to kilojoules. And then the last step that we're going to do is we've got to get to delta H. The only way to get to delta H in calorimetry problems, at least this type of calorimetry, is to first, we've got Q, thank goodness, but now we've got to find the moles of our limiting reactant. Unlike the other reaction, the previous one, for this one, I've actually got to determine the limiting reactant. So note, both of these were 1 molar in terms of concentration. So I'm going to start us, how do we find out which one's the limiting reactant? Whichever one limits the amount of product formed. So I'm just going to go to sodium chloride. So for this first one, I have 1 mole of sodium hydroxide per liter, and we used 50 mils of it, or I did. Again, you've got to be using your numbers here. And so I end up with 0.05 moles of sodium hydroxide. Now I'm going to keep going because I need to find out which one it limits in terms of product. So here we have, for every 1 mole of sodium hydroxide, I produce 1 mole of sodium chloride. So lo and behold, I end up with 0.500 moles of sodium chloride. You're going to do a similar calculation for hydrochloric. So for me, I ended up with the same concentration here of HCl per liter. We used the same volume. I ended up with the same number of moles of hydrochloric. And here, it stays 1-to-1. For every 1 mole of hydrochloric, we produce 1 mole of sodium chloride. So lo and behold, I end up with 0.05 moles of sodium chloride also. You may not end up with this. It depends on your volumes. If you use the same volumes though, look and lo and behold, both of these are limiting reactants in this situation. That's fine. That means we can use either one of those. So I've got Q. Now I can divide by the moles of my limiting reactant. I can choose either one. It doesn't matter. It's going to give me the same value. If, though, one of these is smaller, that one determines your limiting reactant, and that is what you will divide your heat by to get your enthalpy. Again, watch your sign values, because here you have to think about, did the system lose heat and the temperature went up, or did the system gain heat? So you've got to think endo or exo, because you will have to sign whether it's positive or negative. If you don't have it, it's wrong. Now, I want to talk about number 4. So if you'll come to number 4 briefly and go back to the board, notice we have a solid, so you're going to have roughly 2 grams of mass. You have hydrochloric, which you use, I think, 55 mils. We should also note that the mass of the solution here is going to include the sodium hydroxide, the hydrochloric, but it also includes 45 mils of water. We don't see it in the reaction because it's there to facilitate it. It's an aqueous solution, but this mass of solution over here should be roughly 102. If it's not, then you've done some calculations erroneously. It should definitely be close to 100 at least. And then you've got your delta T and your delta H. Again, your delta H is determined by the heat divided by the moles of limiting reactant. So you've also got to do the calculation to figure out, is sodium hydroxide solid or hydrochloric acid your limiting reactant before you find delta H. So we have one next piece, and it's this last piece right here. And I'm going to briefly walk through it. So let's see if I can get rid of some of this. One of the things I love about this lab is it gives you some extra practice on how to do or how to find enthalpy for calorimetry problems. So from that perspective, think of it as more practice, and the more practice, the better you get, right? So let's look at this. Let's come back to the board over here. Actually, not the board, but the overhead. You've got, it tells you, show how the data for reactions 2, 3, and 4 represent Hess's law. Mathematically manipulate the equations for reactions 2 and 3 so that you generate reaction 4. So here, in this spot, you're going to write the reaction 2 from your lab report form, and then you're going to write the delta H that you calculate for it. Here, you're going to write the reaction for equation 3 from above. And this is the delta H for it. And then this is the net reaction. So you're going to add reaction 2 and reaction 3 from these lines to get to reaction 4. Reaction 4 should look just like this reaction 4 that you did above. Now, you're going to calculate this delta H from these two. Hess's law indicates that we should add these two and we'll get our new delta H because we've added the reaction to get the overall. So this delta H that you calculate here should be fairly close to the delta H that you calculate up here from reaction 4. So keep that in mind. And then it says find the percent difference between the calculated delta H from Hess's law. So looking at that, so I'm going to actually go a little bit further on this. Notice that your reaction, because I'm not sure all of these are here, so I am going to go ahead and show you a little bit. So this is reaction 2. And this is reaction 3. I know this is a long video, y'all hang with me. Just a little longer. So you've got these delta H values. Again, this is what you calculated above, so you don't have to do new calculations for that. Now to add this together, just like in the alum lab, if you see it on both sides of the equation in the same phase, you can get rid of it. And you'll notice when you add that together, it looks just like the equation in equation 4. And then here, for delta H, overall, it is the sum of delta H2 and delta H3 above. Okay? That's what that looks like. Now for the bottom, I'm going to write this percent difference a little different. I'm going to write it like this. You're going to use the delta H of your reaction 2 plus 3 minus the delta H of reaction 4. Now notice, that's not overall, that's reaction 4. Divided by, so you're going to do that calculation, divided by the delta H of reaction 2 plus 3 plus delta H of reaction 4 divided by 2. So make sure you do those two separate calculations. And then you divide them by one another, multiply that by 100, and that's going to give you your percent difference. So this delta H 2 plus 3 is from this overall. This delta H is from your lab report form. Delta H 2 plus 3 again, overall. This delta H form from the earlier part of your lab report form. All right, so make it happen.